Okay. So back to convolution, back to Laplace transforms, and I remember one thing that I forgot to say in my previous Laplace transform review. You may have noticed that Laplace transform takes a function of t, and it gives you back a function of what? Function of s, right? Yeah. See, our definition is that f of s is, which we call it as the Laplace function, Laplace transform of f of t, which is 0 to infinity of f of t times e to the negative st dt. And because t is integrated away, this integral result depends on the variable s. So you end up with a function of s, right? And there are some things that take function to a function, but sometimes those are called a transform. And the ones that are called transform takes a function of one variable and gives you back a function of a different variable. That's called a transform. Okay? On the other hand, if you take a derivative of a function, if you have a function of x and you differentiate by x, you still get a function of x, right? Yeah. So those things are called operators. Okay? You have, I want to talk about convolution and Laplace transform. So let me first talk about what a convolution is. So if you have a function of t and another function of t, the convolution of two things is the following integral. It's integral from negative infinity to infinity of f of t times g of, f of x times g of t minus x dx. That's called a convolution. Yeah. So, well, what does that mean? It means that see, if you have y equals to t minus x, that's like, here's t, and here's t is like the y-intercept, and slope is -1, -1 times x, right? So what's happening is you evaluate the function at given x, okay, and you multiply to the value at t minus x, and you're multiplying the two. Trying to make sense out of this. For a fixed value of t.
Can we use different variable other than x?
Yeah, it's just it's supposed to be you multiply things in here. Right. Or here, x and then y. Yeah, so for a fixed value of t, what's happening is you're multiplying. You're adding over this edge. Sorry, I suddenly got confused myself, right? Okay, well, I'll have to think more about this one. Okay. All right, so that's called the convolution of two functions. And one thing that you could prove is that if you take u to be t minus x, so that x would be t minus u, if you bring the x here and move the u there, then the integral becomes, this becomes u and this becomes t minus u, right? Okay. And then these two will interchange because when x is infinity, u will be negative infinity, and vice versa. So this will be negative infinity top and infinity on the bottom, but then du is negative dx, so there's a minus that's extra, which can be used to flip this back again. So you can prove that this is the same thing as integral from negative infinity to infinity of f of t minus u of g of u du. But what's that? That's exactly gt convolution f of t. So in other words, convolution is a symmetric operator. Okay? F convoluted with g is the same thing as g convoluted with f. So that's one thing. Now, however, when when Laplace transform is considered, we have the Laplace transform f of s defined as integral from 0 to infinity of f of t e to the negative st dt. And if you look at this definition, you see that you're not using all the information about f of t. You're only using the value of f of t from 0 to infinity, right? So if you had two different f1t and f2t that had different values at negative side, but if their values are agreed on the positive side, they will have the same Laplace transform. Do you agree?
Can you say that again?
Let's say ft is like something crazy and then like that, okay? And f2t is like 0, but then same. Then their Laplace transform will be the same because you only use this right side.
Yeah.
Right? Okay. Yeah. So what that means is that you don't, you have some ambiguity here, but if you assume that f of t, all these functions are 0 for negative, then the Laplace transform will be unique. That's how we can use the Laplace transform table. We know that if one thing has Laplace, so for example, if I have 1, then the Laplace transform of 1 is 1 over s. Now we know that the inverse transform of 1 over s is 1 because we are assuming that on the negative side it's 0. Okay? So when we say the inverse transform is 1, we're really saying that on the right side we know that the value is 1, but the left side can be anything, but let's just agree that it's 0. Okay? So because of that, oftentimes you have to involve convolutions that have 0 outside, 0 on the left side. So, so if f of t and g of t are both 0 for t less than 0, okay? Then here's what happens with the convolution. ft star g of t. First of all, when x becomes negative, it doesn't give you anything, right? So this negative infinity can be changed into what? 0. Okay? Because of this part, right? But then, here's another problem. If x goes x becomes bigger than t, what happens? This would be what?
0.
Yeah, if this value would be negative, so g of that number will be 0, right? So x can only go up till
0.
t.
T.
Yeah. X cannot go. If x becomes bigger than t, then this will be 0. So this is another formula for convolution. Right? So in the literature, sometimes you would read a book and they say the convolution is this one. But in some other books, you might see that the definition of a convolution is this. And it really depends on the context. Here, when you see this one, you're often working with a case where you don't allow functions to have any values before 0. Okay? If you only have functions defined for positive part, then you cannot discuss the negative part, so you just do this. Okay? And that will be our case for the Laplace transform. This is what we're going to use. Okay, so with this definition, what do I want to prove? Well, here's what I want to prove. I want to prove that if you have a Laplace transform of ft star gt, then it's going to be f of s times g of s, where f of s is the Laplace transform of fs, and capital G, the ft, capital G of s would be the Laplace transform of gt. So Laplace transform changes convolutions into products. And if you recall, we were using Laplace transforms to solve differential equations, right? And sometimes you might end up with a case where you're trying to invert something that looks like a product. Then this formula says, oh, if you want to invert a product, you just have to take the convolution of them. And that's going to also have some other meanings. Right?
Do you mean there are f and g are orthogonal?
F and G are what?
Orthogonal.
So what?
Orthogonal.
No, not orthogonal. No,
Okay.
no. It's just that they're multiplied. If you have a product, the inversion becomes a convolution. And hopefully I'll have time to show how it applies. Right? Okay, so let's show you the brief proof. Okay, so what's the Laplace transform of f convolved with g? Sometimes they write t only once, just like that. Well, we know that Laplace transform is integral from 0 to infinity of that function times e to the negative st dt. But then the convolution itself is integral from 0 to t of f of x g of t minus x dx. Okay? And then since this doesn't have x in there, so in the view of this integral, this is just a constant. So any constant can be brought inside the integral, right? So what we have is the integral from 0 to infinity of from 0 to t f of x times g of t minus x times e to the negative st dx dt.
Oh, t is constant, right? T is a constant?
In the view of this inside integral. It's not a constant in the view of dt. It changes, but I'm just saying that this can be brought inside. This cannot go outside because in terms of dt, this is not a constant, but this can be brought inside, so that's what I did. Right? Okay. Now, what I would like to do is, and you'll see why later, I want to switch dx and dt. Okay? I want to change the order of integration. And I'm thinking of this as a double integral. So
So we switch the integral and we switch the dx.
It's not as simple as that, right? We can't just simply switch these two around. And that's what you learned in multivariable calculus. If you are a good student in multivariable calculus. Okay, you're not. All right. That's fine, because we'll try to do that, okay?
If it's continuous,
Huh?
if it's continuous, we can switch it. Right?
Fubini theorem, something like that. I'm not talking even about that. I'm talking about how to change these two. The bounds change. You have to figure that out. Okay? So, look, if this is dx, this should be really thought as x equals to 0 and x equals to t. Okay? And these should really be thought as graphs. Okay? So how did you learn changing order of integration to d? Well, usually it was y and x, right? So you had like x and y, but in our case it's x is a function of t, so instead of x and y, we'll need x and t. Okay? So x is a function of t. So that x equals to t is, what kind of graph is x equals to t? So just replace x by y and t by x. What kind of graph do you have? X equals to t would be?
Straight line.
Straight line. Which line? Draw it up in the air.
Going through the origin?
Going through the origin, which direction?
Y equals to x.
Yeah, it's like y equals to x. X equals to t is like y equals to x, right? Okay. X equals to 0. What is that? Remember, x equals to 0 should be really thought as y equals to 0. Y equals to a number is a vertical line, right?
Yeah.
So, y equals to... No, y equals to 0 is a horizontal line. What am I saying? It's this. Okay. So this one's x equals to t.
Yeah.
And this one's x equals to 0. Okay? And the way you interpret this is you start from a point on this line, and you end up at a point on this line with increment in the direction of dx. So your dx would be going this way. Dx would be, x is this way, so increasing in dx means that way, right? So you start from a point here, and you arrive at this point, and you're adding them as you do that. Okay. So that's what this means. So what you're doing is you're doing that for every point, where now t goes from 0 to infinity, right? 0 to infinity. So the domain that you're integrating is this domain. Is that okay? Mm-hmm. So when you see this 0 to infinity, x equal to 0 to x equals to t should be this line to that line, where the t varies from 0 to infinity. So that's the domain of integration for this double integral. Okay? Now I want to change this into dt dx. So the inside wouldn't change. It's still f of x, g of t minus x, e to the negative st. And dt goes inside, dx goes outside. And then, because now dt is inside, things in here should be t equals to a function of x, and t equals to a function of x. And then you have the x values, right? And dt in this picture is, t is this direction, right? So dt is this way. So in other words, let's say you have a part-time job during the summer, okay? And of all the jobs, you got the job of painting houses, right? And once one client calls you to a room and says, hey, here's the picture I want, okay? I want you to paint this domain, right? And you're given two choices. Either you can brush upwards or brush rightwards, okay? Those are the two choices, all right? Which one are we doing? We're trying to brush rightwards, because I have dt chosen inside. So dt is inside, right? So we're trying to brush this rightwards to paint this. So if I do this, where do you begin?
0.
No, you begin on this line. What is this line?
X.
X equals to t. So what should I write here?
X.
T equals to x. Okay? Equals to x. Okay, where do you end?
T equals
Infinite.
Infinity. So you go from x to infinity, right? And then x goes from where to where? Now once you've painted this, now you just have to figure out which level the paintbrushes should be
From
at.
0 to
0 to infinity, right? So x goes from 0 to infinity. So these two intervals are the same thing. It's just a matter of this one is trying to paint that same region upwards. This is like painting region on the rightwards. You know, it's a big challenge teaching this class because I basically have to teach you Calc 1, 2, 3, 4, everything.
Even learned that.
I mean, what did you remember from all the previous classes? It's like, this should be common knowledge at this point, but nobody seems to know, right? Okay, well, anyways. So now here's what I want to do. Now that the integral is dt, I have something nice going on. See, f of x is now considered as a constant with respect to dt, so I can bring this outside. Okay. Moreover, eventually I want f of x, right? I need the Laplace transform of f of s. So what I do is I rewrite this as integral from 0 to infinity of f of x times e to the negative sx. Okay? I do negative sx, integral from 0 to infinity, g of t minus x, e to the negative st, but I have to undo this, so I put e to the positive sx, dt dx. Okay. And you know, this is same as the previous one because again, e to the sx is considered as a constant in the view of dt. So if I bring this outside, it's going to cancel with this one. So it is indeed the same thing as this one. Agreed? All right. And then I'm going to do a change of variables here with, see, e to the negative st, e to the sx is same thing as e to the negative st minus x, right? These two are the same. So I can take this one and replace t minus x by u. So I'm going to use u equals to t minus x. So that du is, what's du? dt, yes, that's, yeah, I was going to yell at somebody if they said dx. So you were doing dt, right? So du is dt, not dx. Okay. The variable is t. X is a fixed constant here, okay? Yeah. X is a constant, t is the real variable, so du is dt. So dt can be just changed, dt could be just changed as du, because they are the same thing, right? So, let's see what that integral will give us. So what we have is 0 to infinity of fx e to the negative sx. Okay, another thing. If t is x, what's u? When t becomes x, what's the value of u?
0.
0, because if t is x, x minus x is 0. So this one starts from 0. Okay. And then when t is infinity, what's u?
Infinite.
It's still infinity. And you have g of u. E, I said this is e to the negative su du dx, right? But now look at what happened. By doing the change of variables, this is now free from x, right? So this is just a constant. It doesn't have any x in there. I can bring that outside the integral at no cost. Right? So here's what we have. We have the integral from 0 to x, f of x, e to the negative sx, dx, times integral from 0 to infinity of g of u, e to the negative su, du. But then, now these are separate integrals. Sorry, it should be infinity. Now these are separate integrals. It doesn't matter whether you use x or t. So if you replace these x by t, this u by t, then what does this become? What is this?
Fs, the big Fs.
Big Fs, the Laplace transform of little ft. What's this one?
Big G
Yeah.
of Gs.
So that proves this, right?